So we just finished a unit on looking at how the derivative plays into, or the derivative's role in um, defining what a function looks like. Okay, so there's so much more that we can use a derivative for other than just, hey, what does this graph look like? And one of those applications involves velocity and acceleration. So let's just take a minute and look at this slide here from this PowerPoint. An object in motion, moving along a line, right? We can represent this object's position in one dimension with a function p of t. Okay, so some books will use s of t for position. This book uses p of t. If we want to know how fast the ball is falling, we can take the derivative of this. Okay, so we find the ball's velocity in meters per second. And again, p of t is position, v of t is going to be velocity. Sometimes we refer to velocity as p prime of t. If we don't care about an object's direction, we're talking about the speed. And the speed is just the magnitude of velocity or the absolute value of velocity. The velocity is the rate of change of an object's position over time. Acceleration is the rate of change of an object's velocity over time, and we denote that with a of t. So pretty much what we have is, and I do this from time to time, so we have the position, the velocity, and the acceleration, and in order to get from the position to the velocity, we have to take the derivative. And in order to get from the velocity to the acceleration, again, we take the derivative. So we refer to the acceleration as the second derivative, right? And the velocity is the first derivative. And we're talking about the first derivative of position. Just a couple of things to note here. This is all going to be motion along a line, okay? And one of the things you might think about when we're talking about this would be a spring that has an object right here, right? So we have an object right here, and we have a spring connecting that object to some table or something, right? And if we pull this object down, right, then our spring is going to elongate like this, okay? And then I'm going to let that thing go, and that object is going to go up and down and up and down. And so it's traveling along a line, right? And so you'll see this in some physics classes that you may take along the way. P of t is going to be the position of the object at the time. The velocity is v of t. Speed, this is what we mentioned a minute ago, is the absolute value of velocity. And then acceleration. So acceleration is the first derivative of velocity, and it's the second derivative of position. We'll take a look at a problem here. A ball is dropped from a height of 80 feet. So in this case, we're talking feet per second, right? Its height above the ground after t seconds is given by the position function, negative 16t squared plus 80. Find the velocity and acceleration functions of the ball. In other words, this is just a fancy way of saying what is the first derivative of p of t and what is the second derivative of p of t. So if I'm finding the velocity, the first derivative, that's negative 32t, right? Because the derivative of 80, that's a constant, is just 0. Well, that makes the acceleration here negative 32. So if we used our units here, we would be saying the velocity is negative 32 feet, negative 32t feet per second. The acceleration is feet per second squared. Okay, and by the way, this is a constant, right? This is the constant due to gravity, and it's in feet per second squared. If we're working in the metric system, typically we refer to gravity as 9.81 meters per second squared, just in case that comes up a little bit later. So here's a question. A ball is tossed up in the air. Its height above the ground is given by the position function, this guy. What's the ball's instantaneous velocity at t equal 2? Well, the instantaneous velocity implies that we want to know what the derivative is, right? Because we're looking for the velocity at that moment in time. We already know a function or an equation for the average velocity, right? The average velocity is just the position at t final minus the position at t initial over t final minus t initial, right? It's the displacement the change in x, the displacement over the change in time. Our question deals in instantaneous velocity. So we need the derivative of this, right? Well, the derivative of negative 3.8 t squared plus 4t plus t is given by this equation right here, negative 7.6 t plus 4. So to find that instantaneous velocity, we're just plugging in 2 for t. And that's what we've got in this line right here, negative 7.6 times 2 plus 4. So our instantaneous velocity is negative 11.2 meters per second. So there are a couple of things that we can say about this, this instantaneous velocity. One of those things that we can say is that the object's motion, object is moving to the left or down. And I know that because of the negative sign that's indicated here. So that negative sign on velocity indicates the direction of motion. Because this ball is tossed up in the air, we know that after 2 seconds, the velocity is negative. This object is traveling down. Okay, so that's the only true thing we can say about the position or the motion of the object is that at 2 seconds, the object is moving back towards the ground. When we talk about motion of an object, there are some things that we need to keep in mind. What kind of information can we pull from the position moving along a line? We can derive the velocity and acceleration. The velocity tells us the speed and direction in which the object is moving. If you remember just a minute ago, we were talking about that, right? So we say if the particle has a positive velocity, it's moving right. If the particle has a negative velocity, it's moving left. In this problem, the position of a particle moving along a coordinate axis is given by this equation. I want to know what is v of t, at what time is the particle at rest, and on what time interval or what interval is the particle moving from left to right, and what about from right to left? So this may involve a little bit of discussion, and there's a whole lot of discussion about this problem on the next page. So let's just go through this. If we want v of t, we all know that we're going to take the derivative. So the derivative of t to the third, t is 3t squared. 3t squared. These are our favorite type of derivatives. They're fairly easy, right? Plus 45. So this is that velocity function. You can see it down here. The next question is, at what time is the particle at rest? So to answer this question, right, at what time is the particle at rest, you need to think about what that means to be at rest. To be at rest means that the velocity at that given time is 0. So if I want to know when is the particle at rest, I'm going to set the velocity function equal to 0. That's what we've done here. All of these numbers are divisible by 3, so we can make our problem a lot easier to work with if I take that 3 out and divide both sides by 3. It goes away. What multiplies, oh goodness, what multiplies to give me 15 and subtracts to give me 8, that's a negative 5 and a negative 3. So we figure out that when t is equal to 5 and when t is equal to 3, the object is at rest. Well, here's what that means. The particle is at rest and could change directions, right? So if you think about a ball's flight through the air, okay? So let's imagine that you picked up a ball and just chunked it as far as you could, right? The ball's flight path might look something like this, and it's going to top out and it's going to come back down here, right? Well, what happens at the very top, what happens right up here, is that there's a point where the ball just kind of goes up and it sits there for a second and then it comes boom back down. And if you watch golf, which, you know, I don't watch a whole lot of golf, but I have seen enough golf balls hit to know that the typical flight path for a golf ball looks kind of like this, right? And it goes up and it'll kind of sit and then it falls. Okay, so what happens is it's sitting right up there at the top for just a brief moment in time. The velocity of that object is 0, okay? Well, when that velocity is 0, that means it's going to come back down, right? So we have the object moving up with a positive velocity, and then we have the object moving down with a velocity that's less than 0. In the second part of this problem, on what time intervals is the particle moving from left to right? In other words, that's just a fancy way of asking this question. We'll get this color ink here. On what time intervals is the object moving from left to right? Okay, left to right indicates this direction here. This is an object moving to the right, which implies that the velocity is greater than 0. And from right to left would be this direction, and that implies when the velocity is less than 0. So what we're going to do is we're going to set up, I'm going to set up one of those tables, kind of like what we did in that last section, right? So we're going to start right here with 0 and go to 3. And then I'm going to have that time interval from 3 to 5. And then we're going to have the time interval from 5 to infinity, because we know this object begins flight when time is equal to 0. So if we look to see what is the value of the derivative maybe at 1, and what's the value of the derivative at 4, and I keep putting f prime, and because of our application in here, I probably would be better suited to put v. Just v, not v prime, just a regular old v. In other words, what is the velocity at 1, the velocity at 4, and what is the velocity at 6? So our velocity function was 3t squared minus 24t plus 45. And you'll notice that got a little autosave going on. You'll notice that right here, the PowerPoint chooses to put 0 in, and that's fine because our domain indicated that t would be greater than or equal to 0. I choose to put 1 in just because I want to make sure that I choose a number within that domain. Using the endpoint doesn't always work. Plus 45. So if we look right here, 3 minus 24 is a negative 21, and negative 21 plus 45 is a positive value. Again, I don't care what that positive value is. I just care that it's positive. This indicates that the velocity is positive or greater than 0. The object is moving from left to right. So when I plug 4 in, right, I'm going to have 4 squared, 24 times 4. So if we do the math here, we're going to wind up with a negative value. A negative value indicates that the object is moving from right to left. In other words, it's moving towards the left, from right to left, and that is a negative velocity. And then plugging in 6 for our velocity gives us a positive value. So again, there's another situation where the object is moving from left to right. Okay, so we can answer the question in this manner. Go back. So we can answer the question. The object is going to move from left to right on these intervals, 0 to 3, union 5 to infinity, and then it'll move right to left on 3, 5. One more question here. A particle moves along a coordinate axis. Its position is given by P of t. Is the particle moving from right to left or left to right at time equal 1? Again, just interpreting what our question is asking. And so what I really want to know is, what is the velocity at time equal 1, right? If it's positive, we're moving left to right. And if it's negative, we're moving right to left. Okay. I don't really like this better. I like showing left with the arrow pointing from right to left. So in this one, right, we find the derivative 2t minus 3. The velocity at 1 is just going to be 2 minus 3. Now, what I've done is I've gone in, and all of these problems are involving the power rule. But you could have problems involving trig rules, the chain rule. All of those velocity and acceleration questions can be applied to any function that we have, and by now you know how to take the derivative of those functions. So as you go throughout the homework, just keep that in mind. And as always, reach out. I'd love to help you out in person if you need it.